Couple of things. First off, give me some homeworks. Zoom. Let's play. Coming up, the 8384 is due tomorrow. All right, which so the 8384 is homework is due tomorrow. We're gonna jump back into that. That was on polar coordinates. We were almost done with that. And then we'll move on to the next section. So, in any case, last time we were talking about polar coordinates, and basically we're using r and theta rather than x and y to get points on the Cartesian coordinate plane. And we can graph in polar. We can convert from polar to rectangular and back and forth. We can convert equations. And then the last thing we were doing is we were graphing. Remember, r equals 6, r equals 5 sine theta, r equals -8 cosine theta. Those all gave me circles of different types. Okay. If A is positive, the radius is A over 2. If A is negative, the radius is negative A over 2. On these last two, I should have said that in the slides, but get what I'm saying, where I'm going with that. Lines through the origin all look like theta equals an angle. So we have this polar graph grid that sometimes people use. Okay, I don't typically use that. We looked at these, and these were like the limicons. We had the cardioid when A or B were equal, and then we had an inner loop and a dimpled one, depending on the relationship between A and B. If A is bigger, then it's dimpled. If B were bigger, then we have an inner loop. But it's these bean-shaped objects. Remember that? I was at the very, very end of last one. And we were playing around with this on Desmos. Here. And again, I can say A and B. They're both, let's say, 5. We should get our cardioid. And then if I start increasing B, I get an inner loop. If B is bigger, if I start decreasing, then it becomes dimpled. If I decrease enough, moves over to the other side when we get negatives. And at -5, I get a cardioid facing the other direction. And I'll get an inner loop facing the other direction with like a negative, something bigger than 5. Negative number bigger than 5. So that's what we saw last time. Obviously, here we have cosine, so we're oriented along the x-axis. If I change the cosine to sine, then I'm oriented along the y-axis. All right. And remember, last time we said when we're graphing a polar, a lot of times the x-axis is called the polar axis. The y-axis is called the line theta equals pi over 2. Now, what we're going to look at now is, I should say, these types of graphs where we have an argument inside of cosine, which is something like 3 theta or 5 theta or 7 theta or -5 theta, something like that. And then we'll do the same thing with even values inside of that argument. And then we'll put coefficients out front and play around with those. Again, I'll do this on Desmos. I'll show you how to do it on the graphing calculator as well. There's an interesting thing on the graphing calculator that happens. We don't need to do that. So if I do R equals, let's just do 5 times cosine theta. That was the one circle laid out on the x-axis, right? That's if we have 1 theta. What if we put 3 theta in there? It turns out if I put an argument of 3 theta, you can see that this first loop is still laid out on the x-axis, but we loop back and around, and we get essentially what we call 3 petals, right? This object is known as a rose curve because it looks like, in some ways, a flower with 3 petals, okay? If I put a 5 in there, then I get a rose curve with 5 petals. Notice that still we have this one loop laid out. My initial loop is this one, laid out on the x-axis or the polar axis. Okay. What do you think is going to happen when I change it to 7? We're going to get 7 petals. And if I change that to 9, we end up with 9 petals. And if I change that to 31, if you counted that, you should get 31 petals. All right. With, as you can see, one of them laid out right along the x-axis. So we have 5 cosine 3 theta. We see that the 3 theta, if we had 3 theta or 5 theta or 7 theta, that tells us how many petals. Notice what's happening with the coefficient of 5. 5 tells me how long this petal is, right? It's 5 units long, that petal. If I would switch the coefficient to, let's say, 7, then that first one would be stretched out 7 units. Another way to think of this is since we have 7, we'll put 7 as a radius of a circle. That rose curve is inscribed inside the circle of radius 7. Does that make sense? And you'll notice that not only is this petal 7 units long, but also these other 2 petals are also 7 units long. They're all identical, basically. If I were to put a negative coefficient, all it does is flip the rose curve across the y-axis. So we still have our initial petal oriented along the x-axis, but facing in the other direction. What happens if we have sine instead of cosine? Well, then one of my petals is going to be along the y-axis. Makes sense? So there it is. And the same principles here. If I put 5 theta, I get rose curve with 5 petals. If I put 9 theta, I get a rose curve with 9 petals, et cetera, et cetera. Now here's the weird thing. What would we expect if I put a 4 theta there? Go on.
I kind of read ahead, it was double.
Yeah, you end up with actually, when I have an even coefficient on my theta, I end up with 8 petals. So the even and the odds work different, and that has to do with the period of sine and cosine being 2 pi. All right. So when we have an even number like 2, I end up with 4 petals. If I put a 4, I end up with 8 petals. If I put a 6, I end up with 12 petals. If I put an 8, I end up with 16 petals on my rose curve. So that's an interesting thing. But once again, all of those petals are inside a circle of radius, whatever that coefficient is. Here my radius, the circle was in radius 7 because the coefficient was 7. But if I would have put, let's say, 12, then we'd be inside a circle of radius 12, the whole curve would. Each petal would touch the outside of that circle. Okay. So there you go. That's a rose curve. Rose curve where n is an integer. So if we have an integer in front of my angle, cosine of n theta or cosine of n theta. If n is odd, then we get n loops or n petals. If n is even, then we get double that number of petals or loops. Again, these are called rose curves. We'll graph a couple of these. We actually graphed one of these earlier. We graphed where r was equal to 2 theta, if you remember back. That was the very first thing we graphed, plotting some points. If we knew r equals theta, that was our loop. Okay. And if I put a coefficient in front of that, like a 4th, that's what we get. I shouldn't say loop, that was a spiral. Let's call it a spiral. Now, this is graphed from 0 to 12 pi. So you can see that we have a number of spiral sections. So my theta goes from 0 to 12 pi. If my theta went to 32 pi, then we have more spirals, and obviously if my theta went out to infinity, this would just spiral forever. Okay. That makes sense. By the way, what would happen if we went from like negative 12 pi, let's just say up to 0, it's probably easiest to see that. Well, then I'd have a spiral and then go in the other direction. Okay. It'd be a spiral moving in the other direction. So this one kind of spirals in a clockwise manner, whereas the other one spiraled in a counterclockwise manner. Those are called Archimedes spirals. All right. Well, the Archimedes spiral is the r equals theta, and then we just have other coefficients in front of that, makes tighter or more broad spiral shape. Okay, but that's called an Archimedes spiral, r equals theta. There's a lot of other things you can do in polar coordinates that are interesting. Let me show you just one example of something that we kind of dealt with. We had cosine of theta as a single loop. And then when I did like cosine of 3 theta, I got 3 loops. What would happen if I put a fraction in front of theta? Let's say I put, I don't know, 5/13. I get a really strange looking object. Again, this is from 0 to 12 pi. I went, because we have this weird 5/13, I'm gonna go a little bit further than that. Let's go to 24 pi. So I get this shape. Very, I don't know, looks like embroidery or something like that, right? Some crazy symbol. Let's say we went to 5/8. Then we get this pattern. Okay. Or if we did 5/7. I don't know why I'm using 5 as a coefficient. 5/7. What about 1/7? Looks like that. Or 2/7. Like that. So we get some very, very interesting shape if we put fractions in front of the theta. That's all I'm saying. So you can get lots and lots of interesting curves. That's all. That's all I'm saying. Okay. So that's the end of the 384, the polar coordinates section. I just want you to be able to graph those. Now, obviously, we won't have access to Desmos when you're doing your homework and stuff. So there are a couple things to mention about using your calculator. There we go. There it is. So last time we talked about using the calculator in polar form, and all you have to do is make sure your mode is in polar form if you are graphing. And then when you hit y equals, you get the polar form of this. Now let's put 3 times cosine of, 5 times cosine of 3 theta. If I graph this, I'll do the standard graph. It looks like this shape. All right. Again, this is on our standard zoom, so this is stretched out a little bit more in the x direction than it is in the y direction. Okay. That would be inside of this perfect circle if we graphed it using the square feature. Now, here's the other thing that I want to talk about. Notice how this graphed it. It didn't quite look as smooth. There's a little bit of like straight lines, doesn't look as smooth right now as Desmos did, right? The reason for that can be demonstrated by just hitting the trace button. When I hit trace, when theta equals 0, I'm at the x value of 0 and the y value, x value 5 and y value 0. And then when I jump, my next point that it traces is when theta equals 0.1309 roughly. How your calculator graphs functions like these is it basically connects the dots between points. And what that means is sometimes things look a little bit more straight line than they should be and not curved quite what they should be. Let's see what would happen if I did 7 theta. Notice how those look like a lot of straight connecting dots. All right. Those all should be smooth, like rounded petals. But they're not because that's how we connect the dots. Or that's how your computer is connecting the dots. Calculator is connecting the dots. If you want it to be a little bit smoother, all you have to do is change the step, the theta step in your window. Let's say we changed it to 0.013. It was 0.13. And then I graphed. Well, I'm going to get more dots, so the graph is going to look smoother because I'm using more dots. Okay. It takes a little bit longer to graph because you're using more dots. It has to do more calculations, but it will look smoother the more dots you use. Is that right? So if your graph starts having these weird, jumps, straight line looking jumps, you might adjust the window so that the theta step is a little bit different. And if I went down here to 0.0013, it's going to be very smooth, but it is going to take a long time to draw on my calculator because it's doing a lot of calculations. Okay. Everybody see that? So there you go. That's the whole thing. All right. Let's move on to the next section. We've done section 8384, and now we'll look at the 8687 section. This is another way to do graphing and another way to graph functions, deal with functions. So this is the idea of parametric functions. We're going to introduce a new variable. Usually that variable is the variable t. On occasion, it'll be the variable theta, but usually it's labeled as t. Since every point on a graph has coordinates x, y, what we're going to do is we're essentially going to travel along that graph. I'm going to give you a value for t, and you'll be able to figure out at that t value, what point are you at? The way that's done is we set x equal to a function of t, and we set y equal to a function of t. So I can say at t equals 3, what point are we at? At t equals 7, what point are we at? And so on and so forth. So we have a pair of equations that are giving us each point. And therefore, each graph will have a pair of equations. This pair of equations is called the parametric equations with parameter usually t. Now, the reason we usually use t is because we think about traveling along that graph, and t is a time variable a lot of times. So often we think of t as time, like at time 0, where would you be located? You can imagine a lot of cell phones have tracking, right? And so you can look up, the path you took if you were, running through the woods, or if you were driving around town today. And you could say, well, here is the graph of my drive around town today. At 8:01, where was I at? At 8:03, where was I at? And that could be given as a set of parametric equations. So here's the grid of town. Where was I at? You were at x value of 2, y value of 1 at 8:01 in the morning. And at 8:03 in the morning, you were at x value of 6 and y value of 8. That makes sense. So tracking where you were at given a specific parameter t. Again, we think of that t as time, but it doesn't always have to be time. Okay. So linguistically, what we're going to do is we're going to parameterize an equation, or we're going to parameterize a curve by creating a pair of parametric equations that represent the curve. All right. So the word parameterize, if I say that, or if you see that, that just means create parametric equation. Now we can graph parametric equations. I don't necessarily need to graph this right now, but I will fill out the table. Let's say we have an x value, which I think of as the output of function 1/2 t squared, and a y value that's 3 times t to the 1/2 power. I'm going to write 0.5 power on the board. And then I'll create a table. If I plug in a t of 0, well, t of 0, I'll get 1/2 times 0 squared for my x value. So my x value will be 0. My y value will be 3 times t raised to the 0 power, which is 3 times 0, raised to the 0.5 power, excuse me. So that would be also 0. So what we're saying there is that t equals 0 gives the point 0, 0. So at time 0, we are at the origin. Let's do a t value of 1. 1/2 times 1 squared gives me an x value of 1/2. 3 times 1 to the 0.5 power gives me a y value of 3. So at t value of 1, that gives me out the point 1/2, 3. If I put a t value of, let's say, 2, 1/2 times 2 squared, 1/2, that 2 squared is 4, 1/2 of 4 is 2. 3 times 2 to the 0.5, I'll give the decimal approximation for that. 2 to the 0.5 is an irrational number. So that's about 4.24. So at t of 2, that's going to give the point 2, 4.24. I'll do just 2 others. I'll plug in a 3 and then plug in a 4. When I plug in 3 into the x equation, that's going to give me 4.5. That gives me roughly 2.0 when I round it, when I plug into the y equation. When I plug in 4 into the x equation, 1/2 times 4 squared is an 8. And into the y equation, I get 6. All right. Again, here we have the point 4.5, 5.2, and the 0.86. And we could plot these if we wanted to. Obviously, we have the origin. We'll make some dotted lines here. That might be too big. Probably 4. So 1/2, 3 is right there. 2, 4.25. Right there. 4.5, 5.20. Right there. 8, 6. About right there. Looks like this pattern. Something like that. Okay. Again, I'm not drawing it as smooth as it probably is, but something like that. By the way, in this case, just so that we know, we wouldn't want to plug in negative values for t because it involved taking a negative value to the 0.5 power. That's like a negative square root. right? So negative values aren't going to work for t. But so it starts at the origin, and then it would continue that pattern on. I could get higher and higher values for t if I want. There you go. Now, this is how it's working. Obviously, if we want, we can plot this out using technology. Let me show you that right now. There'll be something at the end we'll show as well. But turns out you can use your graphing calculator to do this one as well. Okay? Just realized if you push pause on the recording, there'll be an example that I missed. It's all right. Okay. So once again, we're doing, this goes pretty quick once you get used to it. We're doing conversions from parametric to rectangular. There's two tools, the direct substitution where we solve for t and just plug it in to the other equation, and then the indirect substitution. So once again, we're in the direct substitution case with example 3. So I need to solve for t on one of these equations. The easier equation is the y equation in this case. When I say solve for t, I mean t, we're going to have to get t is equal to like a function of y. I don't want t is equal to a function of x and y, obviously. So it's easier to solve for t in the y equation in this scenario. Add t to both sides. I guess I can write that step. And then subtract y from both sides. You'll get t is equal to 6 minus y, or negative y plus 6. And then I'm going to plug in that 6 minus y for t into my other equation. X equals root. I'll write root t plus 3t right now. And then the t gets replaced with a 6 minus y. Make sure you put parentheses around the 6 minus y here, so you don't just get 18 minus y. That's going to be 18 minus 3y if you multiply it out. So this is a rectangular equation that's equivalent to this set of parametric equations. I shouldn't say equivalent. It's a rectangular equation that gives you the same graph as that set of parametric. We did lose some information. We lost the information of time. All right with that? Direct substitution is pretty straightforward. Not too crazy. Let's do another example. Let's do here this example 4. It was 3. All right. X is equal to the square root of t plus 1. And y is equal to 5e to the t power. So we want to convert that into a rectangular equation. On this one, both aren't real easy to solve for, but we can solve with not that much difficulty. I would probably choose the x equation to solve for t. That'd be a little bit easier. Subtract 1 from both sides. X minus 1 is equal to the square root of t. And then what I do is I probably square both sides. So x minus 1 squared is equal to t. So I plug in x minus 1 squared for t into the y equation. So I would just replace that t with x minus 1 squared. And that's it. That's it. That's the whole thing. Now, the one thing I wrote on that slide was watch out for the domain. Okay. It turns out that because of the way these parametric equations are written, only certain x values will be allowed. X values that are 1 or higher. Because the square root of t at most can be 0. Can't plot complex numbers, so not on a standard XY grid. So not when graphing x and y. So anyways, the t has domain restriction where it has to be above 0. That means x is going to be at smallest 0 plus 1. Over here, if I just graph the rectangular equation, I would not have that domain restriction. Everybody see that? And you can see this if you graph both in Desmos, for instance. In the way I showed, I'm going to use the calculator graph, I'll use Desmos. If I did square root of t plus 1 on the outside, and then 3 times e raised to the t power. Even if I put like -12 there, it's not going to work. Oh, I'm sorry. I thought I was projecting on the screen. So there that is. Notice that in red we have here. But if I put y equals, oh, I'm sorry, I screwed that up. It should have been 5 e to the t. There. So y equals 5e raised to the power x minus 1 squared. I'm going to get essentially both the left and right hand side of this curve. Whereas with parametrics, I only get the right hand side. So when we say, well, the graphs are equivalent on a certain domain. Okay. So graphs are equivalent on a certain domain. So there you go. So that's direct substitution. Direct substitution is solve for a variable, specifically solve for t, and then plug that equation you get into the other equation. We could have solved for t utilizing the y equation. I would have had to divide by 5 and then take the natural log of both sides. Okay. And you would have ended up getting x is equal to the square root of the natural log of y over 5 and then plus 1. But there you go. Now again, all of those examples are where we have gone direct substitution. Okay, we'll do indirect substitution in just a moment, but you can also apply that direct substitution on the rectangular to parametric side. If I have an equation like this in rectangular form, y equals 5x squared minus 4x plus 2. And I want to convert this thing to parametric. Well, this one equation is already solved for y. I already have y equals. I have y equals a function of x. So what I can do here is I can set, well, the easiest thing to set is set x equals t. That's an equation where I input a value of t, I'll get out a value of x. And then substitute t for x in that equation. So I get y equals 5 times t squared minus 4 times t plus 2. And very easily, I have a set of parametric equations. And that's it. So if I can solve for one variable in rectangular, then I can just set the other equal to t and then replace, do a substitution. And now I have a set of parametric equations. By the way, this wasn't our only option that we could have done. You could have also set x equals, I don't know, t to the third minus 4 if I wanted to. And then replace every x I see with a t to the third minus 4. So we do y equals 5x squared minus 4x plus 2. And then y would be equal to t to the third minus 4 squared minus 4 times t to the third minus 4 plus 2. That would have also given you the same curve. Although it'd be traced out in a slightly different way. This one, each time I increase t by 1, x is increasing by 1. This time, every time I increase in t by 1, the increase is going to be depending on where the t is at, right? So going from a t of 0 to 1, that might only increase by 1, but going from 1 to 2, that's an increase by 7. 1 cubed, 2 cubed is 8. So we're traveling along this one a lot faster. In other words. And then these two equations give me the set of parametric equations. Is that right? By the way, what's this also implying? This is also implying that there are an infinite number of parametric equations which have the same curve as this, right? You can come up with any type that you want. You could say x is 5t or x is 9t squared minus t. So you could put in lots and lots of different things for x, whatever your mind could imagine. You'd have to be a little bit worried about matching domains, but other than the matching domains issues, you could get that. Put in anything for x. Now, if you can put in anything, most of the time, you should probably put in the simplest thing. Simplest thing is usually the easiest. And on a couple of the homeworks, a couple of the homework questions, you'll be asked to do this. And it'll already say put in x equals t, or put in y equals t for the one equation. All right. So it'll be fairly self-explanatory. Let's skip over example 6 and go straight to example 7. In example 7, we want to convert to parametrics. Convert to a pair of parametrics. We have y squared minus 5y to the third power plus x is equal to 7. Take a moment and try to do this in the simplest way possible by putting one of the variables equal to t. All right. Now, if we're gonna convert this to parametric, a lot of times I start by solving for either the X or the Y to begin with. Okay, you don't have to do it this way. You can do it the direct substitution if you see what's gonna happen. But I like solving for the X or Y to begin with. So I'm gonna rewrite this and subtract Y squared, add 5Y to the third to both sides. I'll get X is equal to 5Y to the third minus Y squared plus 7. Okay. Now I see that we have an equation where X is equal to this. And all I have to do is set Y equal to T. And then X is going to be 5T to the third minus T squared plus 7. And that's it. That's my simple parametric equation. And again, technically you could have put whatever expression you'd like here for Y. You could have put Y is equal to T squared or T to the third or 6T or half T, whatever you want, and then just plug in whatever that is. Okay. Again, there are certain T's, like if you put Y equals T squared, then all of a sudden the Y is restricted to positive values. Does that make sense? You're only going to get positive values for Y. So there are some domain restrictions on some of your equations. All right. But that's pretty straightforward. Let's do one more of these direct substitution problems. Try this one. All right, I won't go around. Let's just go ahead and solve for y. Y is the easier one to solve. If you try to solve for x, it'd be very, very difficult. Okay, we have it's under a square root and in an exponent. That's a real hard thing to deal with. So we'll take the square root of y, set it equal to 5 e to the x. I'll subtract square root of x from both sides. And I get that expression. And then I'm going to square both sides. Remember that if you are squaring this right-hand side, then everything needs to be in parentheses. You could multiply that out, but I'm not going to. It's easier not to multiply it out. So I'll just leave it as is. Now that I have y is equal to an expression in x, I just set x equal to whatever equation that I want. I'll choose the simplest one, x equals t. And then my y value is going to be that expression where I substitute every x value for the t value. 5 times e to the t minus the square root of t minus 4 squared. That's, yeah.
Will we be able to square both sides before we subtract the x?
You wouldn't want to, because when you square this side, you have a middle term. That would be square root of x times y. And so you have x and y together, and it'd make it more difficult. Yeah, so if you square the left-hand side right now, you can't do square root of y, square it, and then square root of x, square it, because there'd be a middle term. It'd be, you'd get y plus 2 times the square root of xy, and then plus x, if you square the left-hand side. But there you go. That's, I feel pretty comfortable. Direct substitution. So for direct substituting, going from parametric to rectangular, then we're solving one of the equations for t, and then just plugging that expression into t for the other equation. Okay. If we're doing that, going from rectangular to parametric, we solve for a single variable and then just make the other variable whatever I want. Usually the simplest option is make the other variable equal to t and then substitute. But you can make it whatever you want technically. So now we're going to move on to the other type of substitution, which is the indirect substitution. Now there's lots of different indirect substitution ideas that we could deal with. But we're going to use 2 from the previous chapter. I should say the previous unit, not the previous chapter. Previous unit. They were in the previous chapter, but. Okay. And those are our trig identities. And these 2 in particular, the 2 Pythagorean identities, the one that involves cosine and sine, and the one that involves tangent and secant. We have cosine squared plus sine squared equals 1 for cosine and sine of the same angle. And then 1 plus tangent squared of theta is equal to secant squared of theta. Those are the 2 we'll use. There's lots of others. We could use technically any trig identity. But These two are the ones we're going to be using in this class. Because they're related to a couple of really nice equations. So let's pretend we have these two parametric equations. X is equal to 6 times cosine of t plus 5, and y is equal to 6 times sine of t minus 2. So we have a pair of parametric equations, one of which involves cosine and the other involves sine. Now, I don't want to do a direct substitution here because solving for t in one of those would be rough. We'd have to use inverse cosine or inverse sine. That's not a very nice thing to do. We'd have like a sine of an inverse cosine. Those get messy. So what we're going to do, if I want to convert to rectangular, is I'm going to solve the two equations for the trig functions. So I'm not solving all the way down to t, I'm solving down to the trig functions. So subtract 5 on both sides. And then divide both sides by 6. I get x minus 5 over 6 is equal to the cosine of t. I'm going to solve the other equation down to the trig function, meaning I'm going to get a trig function sine of t on one side. So y plus 2 is equal. Was that 6? Again, were they both 6
Yes.
coefficients? All right. Let's make sure I wrote those down wrong. Or right, I should say. Did not write them down wrong. And then divide by 6. Okay. We get y plus 2 over 6. I'm going to leave it like that. Is equal to sine of t. Okay. Now here's where the indirect substitution comes from. I've gotten down to cosine of t on one equation, sine of t in the other. Then I remember that my trig identity says that if I take cosine squared of t plus sine squared of t, I get 1. So I will replace the cosine of t with x minus 5 over 6. And I will replace the sine of t with y plus 2 over 6. So replace the trig functions with expressions. So cosine, now you got to remember that this thing is being squared. So when I replace with x minus 5 divided by 6, that's going to be x minus 5 over 6 all being squared. And then the sine gets replaced with y plus 2 over 6 And that's all being squared. Now I could stop here if I want. I'm going to do a couple extra steps just to show you what this is and what we've just found. If I square the numerator and denominator, and then multiply both sides by 36. I get this equation. Anybody know what that's the equation of? I'll put that as my final answer. Well, that's the equation of a circle of radius 6. Centered at 5, -2. Right? A circle centered at the origin is x squared plus y squared equals radius squared. That's the circle of radius 6, centered at 5, -2. So notice that we got that from a set of parametric equations involving cosine and sine. Very interesting thing. Just so we've seen it. If I do this on Desmos, you can do this on your calculator too. I'll do it on Desmos so we can. It's quicker. 6 cosine of t plus 5. 6 sine of t minus 2. You can see where we're at. Centered at circle, centered at 5, -2. And then if you look at the radius is 6. The distance from edge to there is 6. Be okay with that? Count if you'd like, but. Five -2. And then if you count the distance to the edge, 1, 2, 3, 4, 5, 6. All those units. So that's it. That's a parametric version of a circle. And it shouldn't surprise us that it involves sines and cosines, because if we remember, points on the unit circle were defined by cosine theta, sine theta. And we could shift the circle over and make it a bigger radius other than 1 if we want to, or smaller radius other than 1 if we want to, by just putting some coefficients in. Okay, that's basically what we're doing. We're shifting and elongating that original unit circle. I put scalars of 6 in front, that makes it a circle of radius 6. And then the plus 5 in the x direction, moved it in the x direction 5 units. The minus 2 in the y direction, moved it down 2 units. And if we wanted to, if I wanted to just do one loop, I could go from 0 to 2 pi with my t and have one loop. If I went from 0 to pi, I just get the top half of the circle. That makes sense. So that's why it is the way it is. I want you to try this one on your own. Now, this one's not going to turn out to be a circle, so you can, don't worry about trying to make it look like a circle. It's not going to be a perfect circle on this one because we have different coefficients in front of our cosine and sine. But I want you to use that trig identity and indirect substitution to convert this to a rectangular equation.
How many times? Mark. But it's also supposed to be. False.
All right, so people are doing well on this. When we solve this for cosine, I'm just going to do it all in one step. I add 4 and then divide by 2. So I get that as the cosine of t. When I solve for sine on this one, I would subtract 1 and then divide by 5. So that is the sine of t. And then I turn to my trig identity and replace the cosine of t with x plus 4 over 2. Replace the sine of t with y minus 1 over 5. And so, excuse me, I would get the equation x plus 4 over 2 quantity squared plus y minus 1 over 5 quantity squared is equal to 1. I'll leave the squared on the top, but I'll square the denominator just so I can rewrite it. You don't have to, Moodle should recognize if you type your answer in like this or you type your answer like this, Moodle will recognize both. At least it's set to. If you have problems with that, but it's set to recognize both. But that's what you get. Okay. Anybody know what this is the equation of? That almost looks circular form, but one side's longer than the other. So it's a circle that's been stretched out. And what you're going to see is it's going to be what we call an ellipse. All right. So if you've seen ellipses before, this one is stretched out a little bit more in the Y direction than the X direction. It's kind of circular shaped. But again, stretched out more in the Y direction than in the X direction. All right. You could graph that. I'm not going to. There you go. So that trig identity, cosine squared plus sine squared equals 1, gave us circles and ellipses. What if we have secants and tangents? Well, if we have secants and tangents, let's take the exact same concept, but just change to secant of t minus 4, 5, tangent of t plus 1. I want you to try this one, and hopefully it's pretty clear that use the other trig identity on this one, right? Okay. 1 plus tangent squared is equal to secant squared. All right, so let's just go through this. I'll do this quickly. We have the other trig identity, 1 plus tangent squared of t is equal to secant squared of t. You can solve it the exact same way that we did before, except for solving for secant and tangent rather than cosine and sine. And just be careful about which one you do first. When you do cosine squared plus sine squared, if you accidentally rewrite that as sine squared plus cosine squared, it doesn't matter that much. But on this identity, it does matter. 1 plus a number equals, so 1 plus tangent squared equals secant squared is not the same thing as 1 plus secant squared is equal to tangent squared. So just be careful, don't rewrite this. Tangent is involving the y, so we get y minus 1 over 5 squared is equal to x plus 4 over 2 squared. And then if you wanted to, you can rewrite that. You don't have to, but I will just show something and allude to something that's coming up. Okay. I'm going to rewrite this in by subtracting this whole fraction on both sides, by subtracting the whole fraction of the y on both sides. I would get 1 is equal to x plus 4 squared over 4 minus y minus 1 squared over 25. Anybody know what that shape is? That shape is actually called a hyperbola. So if you get there's a conic section called a hyperbola, and that's the shape of a hyperbola. And we can actually graph that, might as well graph it once. Graph the hyperbola, that is. I'll graph it in the parametric form that we just saw, 2 secant t minus 4. And 5 tangent t plus 1. And if you zoom out, here's what you get. You get a shape that looks like, 2 curves pointing in opposite directions. You get that shape here. And just so that we saw the other one, I think it was this way. That's a better drawing of the ellipse that we had in the last example. There's some elongated circular shape. Okay. Now, when we do this in reverse, if we want to go from rectangular to parametrics, using one of these two equations, we can do that as well. When I say these two equations, I mean these two trig identities. Okay. So if we want to convert to parametric, then I'm going to force the equation to look a certain way. And then substitute. Okay, so we had two trig identities that we're using in this section. There's lots and lots others that we could have used, but we're going to keep to these two, these Pythagorean identities. This one, we have things that are being squared and added on one side. So we're going to end up trying to force the cosine sine Pythagorean identity. In order to do that, I need the right-hand side to be equal to 1. So I'm going to have to divide both sides by 49 here. That would give me x plus 3 squared over 49. Y minus 8 squared over 49 is equal to 1. So I just divided both sides by 49. When I divide the left-hand side by 49, those things get squared. So I needed 1 on the right-hand side. The other thing I need is something squared. Now I almost have that. I have something squared over 49. I need to make that into one quantity being squared. So that's x plus 3 over 7 as a quantity being squared. And then y minus 8 over 7 quantity being squared. That makes sense? Now I can set cosine of t as this first quantity, sine of t as the second quantity. The way I'm going to do it is I'm going to set cosine of t. And then I'll solve that for x. And then y minus 8 over 7. I'll solve that for y. Multiply both sides by 7. We'll get x plus 3 equals 7 times cosine of t. Y minus 8 equals 7 times sine of t. Subtract 3 from both sides up here, add 8 to both sides of it down there. And that gives us our two parametric equations, one for x, one for y. I'm going to circle each. Box each. So this is the pair of parametric equations through this indirect substitution. I make it look like one of our trig identities, and then I substitute out one expression for cosine and another expression for sine. Any questions about this so far? Pretty straightforward. Again, like I've said this a number of times, but here are the two trig identities we're using. There's lots and lots of identities out there that you could use that we're not using. Not just trig identities, there's other identities that you could use that we're not using as well. I'll skip example 13 and go right to example 14. I want you to try this example. This is a hyperbola. try to convert this thing to a pair of parametric equations. Thank you. All right, so let's go through this. In this case, we can't use cosine and sine trig identity because we have a minus up there between the squared pieces. And therefore, I'm gonna have to move them over and use this secant tangent identity. Okay. So what I'm gonna do is I'm gonna rewrite that. I'll add this fraction to both sides. Well, let me state this. You can do this one of two ways, it doesn't matter. You can either rewrite your trig identity to be 1 is equal to secant squared of t minus tangent squared of t. So if you want to do it this way, that's fine. And then match it up. This would be the secant squared, this would be the tangent squared, that's fine. Or if you want to move this identity over, so it looks like this matches the original identity, then we can do that as well. So either way, if you want to change the way your identity looks, or you want to change the equation, the way it looks, either way is fine. Okay, I'll change the way the equation looks. And then I know I've kind of changed left and right side. I'll change left and right side so it looks exactly like that identity. That'll be 1 plus y plus 1 squared over 81. I'm going to change that to y plus 1 over 9 squared. And then this one I'll put on the right-hand side. That'll be x plus 7 over 12 quantity squared. All right. I just flip sides. Now we set y plus 1 over 9 equal to the tangent of t, and set x plus 7 over 12 equal to the secant of t. Again, make sure you get your secant tangent correctly oriented. We end up with y being equal to 9 times the tangent of t minus 1, and x being 12 times the secant of t minus 7. And those are our two equations for the parametric form. Is that okay? So that's what I mean by indirect substitution. We have these identities, and so we can substitute out a couple of pieces. And like a puzzle, piece it together. Any questions about that? If I ask you indirect substitution, it'll be one of those two. Okay, one of those two. Yeah, go ahead.
Question. You said we couldn't use the bottom one. I had did that originally and I got the same answers.
With tangent and secant?
Yeah. Or, oh, no, I see. Never mind.
Yeah. It wouldn't give you the right graph if you used cosine and sine. Gotcha. Rather than tangent and secant. That's the. With the cosine and sine, you'd end up with an elliptical shape. With the tangent and secant, you end up with a hyperbola shape. Which we'll talk about the ellipses and hyperbolas. I think it's the last chapter.
But you did say that because we can manipulate that identity, we can just plug, make it more look like the cosine identity, and then just plug it in for that for tangents.
Make it look more. Oh yeah. You could with a subtraction. You could have done this. And then said, that has the one on the right-hand side, so I'll put the one on the right-hand side. And then you could have said, well, now I know that secant is x plus 7 over 12, and tangent is y minus 1 over 9. And you could have, you would have had the exact same equations right here. Yeah. So you could have, I manipulated this equation to make it look like this one, but you could have rewritten this one so you don't have as much manipulation to do. Yeah. All right, the last part of parametric equations that we're gonna go over goes back to the concept or the reason why parametric equations are nice. And that is that parameter of t is often thought of as time, like what point are we at a certain time? And that turns out to have all kinds of applications in physics. If I say, what is the graph of the orbit of the Earth around the sun? Turns out it's elliptical. But the graph is important, but it's also important to say, where is the Earth at this point in time? Okay, on that graph. So you can track object movements in space. All right. So it tells you when you are at a certain point in time. So again, that's very crucial to things like physics and all that stuff. And this leads us to the idea of orientation. Orientation means how things are moving along the curve. Okay. Specifically, what we're going to do is say as t increases, how is my curve, how is it my curve being drawn, or how am I tracing out my curve? So the orientation of the curve is the direction of movement as t increases. That makes sense? So as t gets larger, how are we moving along the curve? It could be left to right if we have a line. Could be right to left if we have a line. If we have a circle, then our movement would be either clockwise around the circle or counterclockwise around the circle. We could be moving from higher to lower, from left to right, all those types of things. So let's take a couple of examples here. And I'm going to show you the easy way to do orientation. The easy way to do orientation is through technology. Let's take this first pair of parametric equations. The x equals -3 times cosine of t and y is equal to 2 sine of t. I'm going to graph that on my calculator because it actually turns out that the TI-84 calculator is a little bit easier to figure out orientation than Desmos is. At least to me it is. So on the graphing calculator, let's graph that. -3 times cosine of t as the x. 2 times sine of t as the y. Oh, I'm not projecting calculator yet. All right. Okay. I'm going to do a zoom square. You can use a zoom standard if you want, that's not a problem. But you see that curve. Now, if you were quick enough, you saw how it was being drawn, okay? If you weren't quick enough, that's perfectly fine. If you were quick enough with our eyes, we could see it being drawn. If you're not, that's fine. All you have to do to figure out orientation is hit the trace button. We kind of did this earlier, we hit trace. And if I push the right arrow, that'll increase my value of t. And I can just watch how the movement is going as I increase my value of t. Everybody see that? Increase my value of t. Let's start at 0. We can see that it's moving in a clockwise direction around this ellipse. Right? So I would say that this ellipse has a clockwise orientation. As you increase, this is clockwise. Now the next equation, next pair I should say, is x is equal to 5 times the sine of t and 7 times the cosine of t. Oh, thought it was down there. So 5 times the sine of t is my x value. This is also going to give me an elliptical shape. Now this one we saw being graphed too, if you're quick enough watching it. But again, if you looked away for a split second and graphed it real quick, you could just go to your trace button. I'll start at t equals 0. And this one's moving clockwise as well, isn't it? So this one is also clockwise. By the way, not all of them that are ellipses are going to be clockwise. You could also have counterclockwise. Let me just show you, if you switch the roles of cosine and sine there, and then in your graph, you can see it being drawn. It's being drawn in a counterclockwise direction. And so it's going around as t increases in a counterclockwise direction. Okay. So some things can be clockwise oriented, some things can be counterclockwise oriented. Oops. Hit the wrong. Don't worry about memorizing a bunch of which one's which. Just graph it and then trace and see how it works. Now, these two are, sometimes it's easy when things are circular shaped to talk about orientation because we have clockwise and counterclockwise. Here we have a couple of other parametric pairs of equations. Now, this one you have to be a little bit careful about. I'll show you what's going to happen in a moment. I've written them down on the board. That's fine. The first pair is x equals 5 minus t squared. And t squared minus 4. If I go zoom, I'll do standard. You see we get kind of a partial line, right? Now, here's where the trick is. Let's put trace. At t of 0, I start right there. As I increase my value of t, we're moving up and to the left as t increases. You guys see that? So if you start at 0 as your t value, you move up and to the left. So as long as t is positive, so when t is positive, the movement is to the left, up and left. Is up and left. What would happen if t were negative? Well, first off, it says I got a domain error. That's not exactly true. The only reason it told me a domain error is because my window doesn't allow me to put negative t values in right now. If I want to put negative t values, all I have to do is change the t minimum in my window and the t maximum. So this is something to watch out for when you're graphing, okay? So the t's, sometimes they'll start you out with 0 to 2 pi. And if you want negative t values, or you want t values bigger than 2 pi, you have to change the window. Now let's graph. Now here I'm going to start at negative 10. And then I'm going to start increasing. Notice that when t is negative and I'm increasing, I'm going down and to the right until we hit 0. And then it goes back up and to the left. You see that? So it basically traveled down, hit this point, and traveled back up. So that's what we would say. When t is negative, the orientation is down and to the right. When t is positive, it's up and to the left. Everybody right with that? I know I wrote that down behind the board, but that's what it goes. So. Now the other set of equations is a little bit more straightforward. That one was weird because both had t squared in it, so it's kind of a awkward movement. My last equation pair is x is equal to negative t and y is equal to t squared plus 2. If I graph that. By the way, if you graph this with just positive t values, you only see half of the curve. So it's important that your window goes from negative to positive. And then if I hit trace, you'll see what happens to my x values. As I'm increasing, notice that movement, my point is moving from right to left. So the orientation, by the way, that's with positive and negative t's. We're moving towards the left on this curve. We're always moving towards the left. So orientation is moving towards the left. Or you could have said from right to left. No, I did this stuff. Just do it. In this case. Does that work? So orientation is just talking about the movement. And the easiest way to do that is graph it, trace how it's moving. Or if you're quick enough to see it as it's being graphed, trace, just see it, how the movement's looking. All right, I will leave there. We're actually done with these sections. So you should be able to do all of the homeworks in not only the 8384, which is due tomorrow, but also the 8586, which is due next week. Okay. Or wait, 8687. I misspoke. Yeah. 8687, which is due next week. All right. I'll see you next week.